This is the second part of the tutorial on analytical chemistry. As you can see in the last tutorial, what we discussed was the properties that help us distinguish between certain gases, and the parameters really like color, odor, and it's because of those that we can tell which one is which. And here you can see we made a sort of table. We did the first three gases, that's O2, H2 and H2O, and here you can see this is color, this is odor, and this line, and then it's a few chemical properties. So now I'm just gonna erase this. Okay. Okay, so after this we'll be moving on to a few acidic gases. Just note that all these three, H2, O2 and H2O, so far they were all neutral gases. Okay, so now moving on to the first acidic gas, that would be carbon dioxide, CO2. Color still not changed really. It's colorless as well. Remember, I'm denoting colorless via this gray. Uh, Odor, it is still odorless. Um, Now, chemical properties. Just writing CHP, chemical properties. Okay, these are the major ones that help you say that this one is CO2 and not XYZ. So the first one, it is acidic. Remember that it's an acidic gas. So if you remember well from the last tutorial, acidic gases will turn blue litmus. So say we had blue litmus here, and they will change it into a red color. So here we have red, and this shows that it's acidic. Now another major property is that it turns lime water milky. I'm going to draw that below over here. This is lime water I'm drawing here, and it turns it milky. um, I can't really show it to you here, but what I can do is just make it oops, make it white over here just to show that it's turning milky. Now I'm just going to explain the reaction behind this chemical change over here. Note that it is a chemical change, it's not a physical change, even though it may sound like one, that it's just changing its appearance, but actually there's a whole chemical reaction that goes on behind that. Okay, so the reaction goes something like this. You have CaOH2, which is lime water. I don't know what that is. Yeah, so that is lime water over here. Of course, you add CO2. What happens is that you get CaCO3, calcium carbonate, and along with this you get H2O. Sorry, I don't have space, but so this is the change that takes place. Due to the CO2, the COH2 changes into CaCO3. That's the compound that you see over here. This is CaCO3 plus H2O. So it's basically that CaCO3 has this milky appearance, which is why you see it over here, while COH2 looks something like this. So that's the chemistry behind that property. Now the next property is also pretty important. Um, you'll see how important it is a bit later. Uh, what it is that it has no effect on KMNO4, which is potassium permanganate, and K2Cr2O7 solution. Okay, I'm just going to first draw KMNO4. KMNO4 is this pinkish purple, and K2Cr2O7 solution would be a shade of orange. I'm going to draw it below. Okay, so the one at the bottom is K2Cr2O7 and above is KMNO4. Now what you need to know here, it's pretty simple for CO2, is that if you add CO2 to this, there is no effect. Nothing happens. Over here you will still, nothing really will happen. It will stay like this. And in the other case, KMNO4 will stay like this. The way to remember which one of these is KMNO4, which one is K2Cr2O7, actually I'll tell that when we do SO2, which is the next gas, because it'll be easier then. Okay. Also, the last property is that CO2 is not a supporter of combustion. Combustion, of course, means, uh, fire, basically. It means lighting, like glowing. For example, a glowing splinter. Uh, that means that it is undergoing combustion. So CO2 is not a supporter. So if you put, say, a matchstick which is glowing into CO2, suppose it's a glowing matchstick, it's actually going to just extinguish and just become just a matchstick. So it extinguishes a glowing splinter. And if you paid attention in the last tutorial, you would realize that this is exactly the opposite of O2. This is exact opposite of O2, because O2 relights a glowing splinter. Okay, that's all there is for CO2, but I'll be referring back to it in the next gas because these two are closely related. Just gonna erase all this before we move ahead. Okay. So the next gas is SO2. In the first video, I gave SO2 as an example of odor. Just gonna write this first. SO2. Firstly, color. We're still, unfortunately, still with no color. I'm gonna make it that shade of gray. It's colorless. Then we come to odor. This is the first one so far that has odor, and it is burnt sulfur. Now I don't know about you, but I associate sulfur, I don't know, for some reason, with the color yellow. So in order to visualize burnt sulfur, I'm just gonna draw a bit of my version of sulfur, and I don't know, perhaps make it look as if it is burnt. I don't know if it looks like it, but you should visualize something like this, and it'll all come back to you. Sulfur dioxide smells of burnt sulfur. It's burnt sulfur. Okay. That is color and odor done. So the last one is chemical properties. Now in this, it turns lime water milky. It's the same as CO2 in that respect. Lime water milky. It is also acidic, remember that. Mr. L, yes. Okay, I'm not gonna draw all of it again, and the reaction is pretty much the same, except instead of CaCO3, you're going to get CaSO4. And there might be a change in the balancing, I'm not sure, but you don't need to know that. You can always draw the reaction and find that out. Okay, so as I said, acidic gas, so it turns blue litmus to red. Another property of this is it extinguishes a glowing splinter. So from these two properties, and also extinguishes a glowing splinter, you can see that so far it is exactly the same as CO2. uh, but now, oh, also one more thing. uh, I think I've been forgetting this. uh, Always when we're talking about litmus here, it needs to be moist litmus. This reaction will only take place when you have moist litmus, or if your compound is hydrous, that is, it has water in it, only then will it take place. So always mention moist. Okay. So it extinguishes a glowing splinter. So it's the same as CO2 here as well. But now comes the difference. In the last section on CO2, I told you that when you have KMNO4 solution, and when you have um, it was an orange K2Cr2O7 solution, CO2 has no effect on them. But in the case of SO2, these are changes which take place. Colorless, it's not gray, it is colorless. And in the case of K2Cr2O7, it actually changes into a green. The way to remember this, um, potassium permanganate, which is KMNO4, I think you may have come across it at home as well. It's used in the kitchen quite often. I think that you should just learn as a pink one, and it turns into colorless. There's nothing much to learn. But over here, K2Cr2O7, you can remember as the Indian or patriotic compound, so to say, because from orange it's turning to green. Well, sort of um, resembles our flag, doesn't it? So that's a way you can remember it. Um, and just remember that this is the only way to tell between CO2 and SO2. These changes will only occur for for SO2. For CO2, nothing will happen. So the pink will remain pink, the orange will remain orange, and that's it for SO2 now. And also one more thing, these two changes take place because SO2 is a reducing agent. I'm pretty sure if you're revising this before your exams, you would have come across this. You should probably know what it is, and you can refer to the other tutorials. I think it should be there in electrolysis, but yeah, I think you should know it by now. So just remember this as a reason why SO2 induces these changes and CO2 does not. Okay.